with Lewis acids and bases. Okay, by definition, an acid for Lewis is an electron pair acceptor. A is for acid is how I remember it. And a base is an electron pair donor, which makes perfect sense because remember Lewis is Lewis structure, so it has electrons. Now, another term that's associated is an acid is an electrophile, and a base is a nucleophile. And if you think about it, this actually works because a phile is a lover. So hydrophilic loves water. A bibliophile loves books. So an electrophile loves electrons. A nucleophile is looking for a nucleus. So a nucleophile has extra electrons, whereas an electrophile is short electrons. And so when we look at Lewis reactions, then remember that aluminum here is happy with 6, so it will accept an electron pair here. Whereas this one here has an electron pair to donate. So this is your base, your Lewis base, and this is your Lewis acid. So what happens is this pair is donated here, and if you'll notice, this is where the new bond is. Now, the trick to Lewis acid base is if you look at this, there's no proton transfer. Ammonia has protons, but they're not involved in the transfer at all. So when you're dealing with Lewis acids and bases, you're not worried about who's got the electrons. You're worried about who's got the electron pairs. So here's the figure here where water is donating a pair of electrons. This is called a mechanism. In organic, you'll get a lot of these. And so what happens is this is electron poor. This is electron rich. So it's going to donate. Once it donates, it rearranges to form this structure right here. Now, over here, this is kind of hard to see. It's really big up there. This is a complex forming. Here is your central atom, which is iron, and we're picking up another proton. And the thing about it is when we're picking up the proton, when we're picking up the molecule, we're not picking up the whole thing. What we're actually doing is we're going to split one off. So there are 6 waters in the middle here. We're down to 5, and then the OH. So the net effect on this one is one of these waters donated a proton here, but we're looking at it from the term of the electron pairs. Now, you will be given an equation and asked to identify the Lewis acid and the Lewis base. But I'm about to walk through individual atoms, and you won't be asked to do those per se because they're much harder if you're out of context. But there's some things I want to point out to you. This one is in the family as NH3. So this is a Lewis base. Okay, aluminum chloride, we saw that. It only has 6 electrons around it, so it's going to be a Lewis acid. We saw that in the previous structure. H2S is very similar to water. It has 2 lone pairs, so it will be a Lewis base. NO2 is kind of a weirdo. I don't know if you remember what the structure of it from before, but it has a lone pair, not a lone pair, it has a lone electron. So remember, that makes it a radical. So the point for this one is radicals really want to pick up an electron, so that makes this one a Lewis acid. Now, this one, because it has no electron pairs, that automatically makes it a Lewis acid. Now, CO is kind of interesting because you look at it and you're like, well, it's got lone pairs there, but notice is sharing 3 pairs. So what that really means is that you don't have enough electrons to give each one. So this one is going to tend to be a Lewis acid because it wants more pairs to go into that. And again, I'm not going to tend to ask you individual questions like this. I'm more likely to give you an equation, more like this format, and that one's a little weird, but more like this format, and ask you to identify the Lewis acid or the Lewis base in it, because it's easier to see who's transferring what in that case. Okay, so that brings us to the end of this chapter, and 17 will start shortly.